to the cloud, which talks about vector valued functions. Now, vector valued functions, they're like we've been talking about. This is just kind of like the formal discussion related to it. The vector valued functions are really just dealing with the case of vectors that involve variable components. All right, so that's in its simplest term. But what it does is it actually creates or traces out entire curves in a three-dimensional system, two-dimensional system too. But in a three-dimensional system, it'll trace out entire curves. Right? So a lot of these definitions that you see here are things that with that kind of context in mind should all kind of feel like they're extraneous. You know, you look at it and say, well, okay, this is all basically saying the same thing over and over again. All right. What we're concerned with is a couple of things. One, how do we take something that is a three-dimensional equation, you know, so something that's got x, y's, and z's in it, and represent it as a vector value function, so in component form, and also the same thing with two dimensions, also, you know, in addition to that. But the other component, the other big idea is how do we do calculus to it? You know, limits, derivatives, and antiderivatives. Right. The short answer is pretty easily, actually, right? Because you made it this far, which means that you have at least some proficiency in doing those things in two-dimensional calculus. So expanding it to vector value functions is actually not difficult, right? What we're going to actually spend a lot of time in Unit 2 talking about is what on earth it all means. Because when you find a vector value function and create the graph, that's one thing, but actually finding the derivative, what does that tell you? What does the antiderivative tell you? What is the limit going to give you? You know, those are all important things that we'd have to dive into too. But yeah. So, but for now, the focus is on the skills. So this whole page here just talks about the background, inputs, outputs, domains work the same way for vector value functions as they do for ordinary functions. There is a conversion from vector valued land to rectangular, polar, and parametric form. As it turns out, the vector valued functions are really just, you know, if you want to oversimplify the concept, and it's dangerous sometimes, but here it works, it's really just parametric equations just allowing for multiple dimensions beyond the second dimension. All right. So if you have those ideas in mind, everything tends to get a lot simpler. All right. So the sketches are pretty easy, but they're also kind of a different problem for a different day in terms of doing it by hand. What I will show you is how to do it on GeoGebra. Right. So because that's where our focus should be at this point, just getting the graphs rather than spending the time to try to make them by hand. It used to be the kind of thing, you know, I can tell you what everything used to be, I guess, but the focus used to be doing it by hand, but now it's more like, all right, do you have an intuitive sense? And just like when you're dealing with learning how to use a graphing calculator for the first time, it's really, it's an opportunity to discover the power of being able to evaluate multiple functions simultaneously. All right, so we're gonna just take a quick look at number 2. I'm actually gonna do this a little bit out of order. Number 2, number 3, and then we'll hop back to number 1 because I want to do the GeoGebra stuff first. All right, so let me get rid of this. That plane, I just wish it was, I just wish it didn't exist. That plane is the default that I know and love. All right, so for a vector valued function, it's really just as simple as using the curve command. So curve, then put in your 3 components, in this case it's 3 components, and then from there you just have to establish what the variable is and what the domain is for the parameter, in this case t. All right, so in GeoGebra, you're using the curve function. You're putting in cosine of t just put parentheses whenever you use t in GeoGebra, put parentheses around it as it applies to a trig function, because, and I think this is limited to just GeoGebra, but I can imagine other software having the same trouble. It thinks you're trying to say cost if you don't put the parentheses there. So just be careful about that. All right. So this is the three components: X, Y, and Z. Then you're indicating what the variable is. So an additional t for the variable, and then the domain. Negative 10 to 10 is where we're going to start. Even though it's a trig function, it's a pretty reasonable way to go, because not all components are trig, right? So it'll allow for all the trigonometric values, but it'll also give us a max and min z values that are pretty finite, negative 10 to 10. So this is our domain for t. All right. So curve. And again, you see what happens there. I get boxed out by the things, so I have to expand my window. Curve, open parens, cosine of t. Just type it in, but parens on the t. Now, there are some graphs where you'd be like, well, it'd be quicker to do this by hand than it would be to just type it in. This is not one of those cases. All right? Creating vector value function graphs in 3 dimensions is a bear. All right, so having the ability to do it using technology is definitely a great option. All right, so cosine of t in parentheses, comma, 2 sine of t, comma, t. Then tell GeoGebra what the variable is. Then tell it what the domain is. I'm saying negative 10 to 10. All right. And so you get that, which looks like, okay, well, that's kind of interesting, I guess. But if you kind of get a nicer angle here, you can see that it looks like a spiral, but more importantly, it's an elliptical. You know, if you get a top-down view there. And let me get some screenshots of this. It's an ellipse that's been kind of stretched out. So imagine a slinky. You know, you take the slinky and then you yank on it so that it's too stretched out that it doesn't conform to its original shape. It's like that, except the original slinky was in the shape of an ellipse rather than a circle. All right, so this is what it ought to be in 3 dimensions. Good looking spiral action. And so my answer to anybody that's like, why do we have to do this on GeoGebra? The short version, you want to do that by hand? Seriously? Yeah, maybe somebody does. I don't know. But that's a whole lot of stuff that maybe you don't want to get into. All right. But the key is typing it in the right way, which I think is pretty standard when you think about it in terms of like, okay, well, how can you avoid screwing this up? Well, don't type it in wrong and you'll be fine. I'm not really telling you something you don't know, but there's a lot going on there in terms of what you have to type in. So be careful with your parentheses. Don't forget that extra t. That extra t indicating what the variable is really the key to the whole dang thing. Right? So it's this one here, indicating what the variable is. Every time I've screwed this up, it's because I forgot to put that in. All right? So just be careful. So number 3, it's asking us to determine if there's any domain restrictions. Now we can actually look at the picture now that we have the ability to do this. But like I wouldn't want to do that. Like that picture, I mean, it's got some trig functions in there. It could be a disaster, right? What we can do instead is look at each component individually. So we have the x component, right? X is equal to 3 tangent t. Y is equal to 4 secant t. And z is equal to 5t, right? If you know your trig relationships, you could figure out whether or not there's any domain restrictions. Now, it did ask us to figure out r of 0, r of pi over 2, and r of 2 pi over 3. So that we can kind of do. I'll just kind of do it as a table. So evaluate r of 0. So I'm plugging in a 0 for each tangent. So replace every t with a 0. Tangent of 0 is 0, so that goes to 0. Secant of 0, well, it's really a question of whether it exists rather than what it is, but secant of 0 is reciprocal of cosine of 0. Cosine of 0 is 1, reciprocal of that is 1. The result here would be 4. And then plug in a 0 for t, and you're going to get a 0. So r of 0 would give you the vector value function, the particular form, 0i plus 4j plus 0k, so 4j, if you simplify. All right. R of pi over 2, tangent of pi over 2 is undefined. Secant of pi over 2, undefined. But it actually doesn't even matter. The last part is great, I mean, 5 pi over 2, but it was irrelevant after I got undefined for any part of it, all right? So r of pi over 2 actually does not exist. All right, so we don't get an answer for that one. So that's a restriction, and that's kind of the point of this question is kind of help guide your thinking, because when I plug in a 2 pi over 3, r of 2 pi over 3, tangent of 2 pi over 3, like maybe you know it off the top of your head, maybe you don't. It's negative radical 3, so negative 3 radical 3. Secant of 2 pi over 3, well, cosine of 2 pi over 3 is negative 1/2. Reciprocal of that would be negative 2, so negative 8. Again, it doesn't really matter what it is. It just matters that it is something, all right, that it actually exists. So 10 pi over 3. By the way, going back to number 2, if you were to create the graph of that by hand, you'd have to do something similar to what we're doing here, just with a ton more points, right? And that's because you need to make a table of values. And if you look at old versions of the answer keys online for this course, on my website, you'll see that there's been some pretty ugly solutions for this kind of stuff, right? But r of 2 pi over 3 would be equal to, and I'm going to write this in component form because it'll be a little bit easier, negative 3 radical 3, negative 8, 10 pi over 3. But again, the idea here is that not that what the solution is, just that there is in fact a solution to begin with. All right. So when we start thinking about whether or not there's a domain restriction, we're really mostly thinking about the instances in which the function, the vector value function, wouldn't exist. All right. So r of t does not exist when t is equal to, so far, pi over 2, but really any instance in which cosine is equal to 0, all right? Because you got to think about, well, what made the tangent undefined, well, tangent sine over cosine. Secant is 1 over cosine. So the instances in which cosine was equal to 0, those were the problem values, all right? So any instance in which t is equal to pi over 2 or any other value that would make cosine equal to 0 would cause this vector value function to not exist. So we would say plus pi k, where k belongs to the set of integers. So the integer symbol is just the z with the extra little diagonal there. All right, you could just write integers. I don't need the notation, but like that's the idea, because then it allows for you to add or subtract multiples of pi. That gets you to 3 pi over 2. It gets you to negative pi over 2, negative 3 pi over 2, and on and on and on from there. All right. Now, if we looked at the graph, which would take a couple minutes to type in, you'd see that it's verified, but you know, the old Tommy Boy quote. But I'd rather take his word for it, you know. So if you know the quote, then you know the part that leads up to that, which I could never say on a recorded video in class, although it's hilarious. You can get a good look at a T-bone, you know, that one. So anyway, I almost said the whole thing just for the hell of it. But that's the analysis that we need to look at when it comes to determining any domain restrictions, because if a graph doesn't exist, then we know that there's no meaningful derivative there, which means that in terms of finding an antiderivative, we have to make some adjustments. You know, if you're thinking of like improper integration from Calc 2, these are all the things that would have to come into play. All right. Now, like I said, we did numbers 2 and 3. Let's go back and take a look at number 1. That's just straight up old school Desmos. It's funny to think of Desmos as old school now. When we're finding a vector valued function in 2 dimensions, it's really just a matter of writing it in as a ordered pair. All right, so coordinates 4t minus 1. So this is right out of the beginning of the course. So 4t minus 1 comma 2t plus 5. And then we just have to establish what a reasonable domain is for this, right? And you can see here that it's only graphed the interval where t is going from 0 to 1. I need more than that. How about negative 10 to 10? So it'll trace out a line and get that in to my notes. But thinking about what that's actually representing kind of starts to help you understand the purpose behind all of this, right? So we just pop that in there. So what's happening is, depending on the values that you've generated for or used to generate a table of values to create this graph, if you were to do it by hand, I can just show you, you know, kind of give you a quick tease. You know, so I'd make a table and say negative 10, negative 9, 8, 7, all the way up to positive 10 if you want. You know, negative 10 to 10, just like we did there. Instead of y1, what I could do is I could say I'm using 4x1 minus 1, and then 2x1 plus 5. All right. So everything in these 2 columns will constitute ordered pairs, and you see some of these values are pretty insane. All right. But if you get a couple of reasonable ones kind of in the heart of the table here, let's say negative 5, 3, I can plot that. So the difference between plotting a vector valued function and plotting points in an ordinary Cartesian plane with ordered pairs is that I'm not just plotting a point and connecting the dots. I'm plotting a point and connecting that to the origin, making a vector. All right, so that's negative 5, 3. So then maybe the next one was negative, that I choose is negative 1, 5. About right, well, exactly right there. Okay. And then let's say the next one is 3, 7. That would be the point over here, roughly here, exactly there. And what we're getting at is the fact that the vector valued function, which is represented by these, this is your set of vector valued functions, but what they're doing is they're tracing out a line, right? This is the vector valued function, right? Each one of these vectors, it just so happens that the ends of the vectors trace out a linear equation, right? So it's kind of a different mindset. But if you think of the vector value function, especially for linears, as kind of like the braces that hold up the bridge that is the vector, the path itself, then that's probably a good way to think about it, right? So, but it's the table that comes from your t values. So we learned in the first unit that parametrics are giving you points along the curve, but when we think about it in the context of a vector value function, it takes on a different meaning, because now I'm concerned with what's holding up that curve rather than the curve itself. All right. So that brings us to the limits and derivatives in the calculus of vector valued functions. It's actually it's very simple, because all you're doing when you're finding a limit, and I'll make complete videos for this so that you can look at the solutions. But when you're finding the limit, you're doing exactly what we did on the previous page at the bottom for each case. If I say that I want the limit as t approaches, for example, 3, all I'm doing is replacing all the t's within my vector valued function with whatever the limiting constant is. All right. So that's why this is like a problem right for the end of the unit, because there's really nothing to it. You know, so the limit of r of t is really just substituting into this 3 squared minus 3t, minus 3 times 2, I should say, plus 4. That gives you the coefficient of I, plus 4 times 3 plus 3, that serves as the coefficient of j. Simplify and you have it. So 4i, 12, 15j. All right. Yeah, it could get a little bit more complicated, and it's possible that the limit doesn't exist, but that doesn't make it difficult. Right? It's really just substitution. Now, there are, like in Calc 1, obscure cases that involve limits. We're not bothering with that. All right. So it's really just a matter of substitute. If it doesn't exist, tell me the instance in which it doesn't exist, like we did on the previous page, and that'll get us at the idea of continuity. All right. So that was the shortest discussion of limits ever, probably. But like I said, I'll put the video together for everything else. If you really want the in-depth, just be on the lookout for that. That'll be up tomorrow. But for the most part, most people only really just kind of need that. Oh, so the rules for limits are the same as they have always been? All right, check. Good to go. All right. Same thing for derivatives. All right. So in the case of number 1, you know, it says state the domain. We're not going to bother with that because we just kind of beat that to death on a previous problem. But if you want to find the derivative of r of t, you're taking the derivative of each component. The only thing is, it's just kind of a function of how much confidence, comfort you have with differentiation. Like if you know how to take your derivatives, you're going to be fine with this. Like the first one's got a little bit of chain rule in it. So derivative of sine t squared would be cosine t squared times the derivative of your inner function 2t. So that's done. For the second piece, you have a little product rule going on there, kind of tough to see. But if you slap a little multiplication symbol in there, it becomes a little bit more obvious. So you have your first function and your second function. So the first times the derivative of the second, the derivative of natural log. So I'll write the rule down because I know this is like the number one thing people forget coming into this course. So d dx of the natural log of u is equal to u prime over u. All right. We're thinking of every test in this class as an open notes test, so feel free to have access, like if you have a table of derivatives available to you, there's nothing wrong with that. Like you've already been tested on that. I don't need to verify that you have instant recall and all that stuff. That's fine. So first times the derivative of the second, so that would be, well, in this case, with respect to t, so 1 over t minus 1 plus the second, which would be ln of t minus 1 times the derivative of the first, which is just a 1. All right, so that's my second component. If it makes sense to simplify, then by all means, but I'm not going to ask you to simplify. The reason why I say if it makes sense to, like if it's one of those cases where you need to type in your answer, sometimes taking a second to simplify, it'll give you less to type in, and there's a benefit to doing that. All right. And then the last component is just another chain rule. So tangent of e to the t. Another thing that people tend to forget, the derivative with respect to x of e to the u is e to the u times u prime. Right? In this case, the exponent is just a t, so that's easy enough. So derivative of tangent secant squared of e to the t times the derivative of the inner function. E to the t has a derivative of e to the t. And so that's the third component. And like I said, if there's no logical reason for you to simplify, then don't bother. All right. In this case, maybe you say, okay, well, these two will cancel, so at least it'll clean up a little bit. But be careful, it cancels to a 1. It doesn't cancel and just leave you with that. I've had people screw that up plenty of times in the past. All right. So there's really nothing new with the derivative, except what are you doing? You're taking the derivative of each part independently of one another. Right. So that's not challenging. The same holds true for antiderivatives. All right. So when you're dealing with antiderivatives, and there's practice on the next page, I'll take you through that, but I'm not going to pull the rug out from under you and throw like a nasty problem like you see on the next page with the dot products and the cross products. So don't worry about that for now. There's a time and a place for that. When we talk about tangent planes and stuff like that, again, unit 2, we'll come back and talk about these concepts. All right. So we're kind of in hyperdrive right now. 1, because I'm looking at the clock, and 2, because I don't want you to be like overwhelmed with the amount of crap that you have to do on this test. All right. So the last thing is the antiderivatives. And again, that's just a function of your comfort level in taking antiderivatives. All right. So you still find the antiderivative a piece at a time, just like you would find the limit, just like you would find the derivative. Sometimes it's going to be easier. In some cases, it'll be easier than others. So you have your 3 components here. The antiderivative of each part. This is an IJK notation, so you can put your answer in IJK or you can put it in component form. It's entirely up to you. I never have a requirement one way or the other, so whatever you're comfortable with. So the antiderivative of 3t squared would be t cubed. plus t squared. Now, it's an indefinite integral, so there has to be an integration constant. But there's going to be 3 of them. So we denote them by indicating the dimension that they come from. So we could say plus c sub 1 or c sub I. Either way is perfectly fine. All right. So it's just that you're going to have 3 potentially different integration constants for each component. So we need to distinguish them from one another. All right. So I'm going to use the component form, 3 over 2 t squared minus 6t plus my second integration constant. If you want to say c sub j because it's the j component, that's fine also. Just some way of distinguishing your integration constants from one another. The last component, 6 over 4, so 3/2 t to the 4th plus 5/3 t cubed minus 4t. Then we tack on our integration constant, this time c sub 3. And there you go. All right. So your ability to integrate is the only thing in question here. All right. And the difficulty level of a question is strictly dependent on the quality of the vector value function, just how challenging the function is. Like in the second one, in B, so you won't, like I said, you're not going to have to worry about derivatives or antiderivatives involving cross products and dot products. So like C is out for now. But B and D are fine. D's a nice one because you could do that whole thing on the calculator, right? But B, you look at it and say, well, I don't know how to take the antiderivative of TE to the T squared. Well, that might be a problem. But just draw on your Calc 2 knowledge. In this case, it's use substitution. So we're looking at x equals TE to the T squared. I would let u, typically you'll let u equal the more complicated part. So I would let u be equal to e to the T squared. You could look at it that way, but then you'd say, well, that's just making things way more complicated. Right? So maybe not the most complicated part, but maybe the second most complicated part. So you'd say T squared. All right. You just kind of, you try something. If it doesn't work, try something else. So when I differentiate that, I get du equals 2t dt. And what that'll do when I'm integrating, so just going to move this up here, is that'll allow me to swap out, instead of a t equals, te to the second power, I can have something in terms of u's. All right, so I already know that I can get this in terms of u, so that would be e to the u. Now I just want to do something about this. So what I do is I just kind of manufacture it. So because again, ultimately, if I can speak, which is becoming more and more difficult as the evening goes on, ultimately we're looking for the integral of e to the te to the t squared dt. We figured out a way to get rid of this guy. That's with the u. So e to the u replaces that. I just need to get rid of the t dt. I have a 2 t dt. If I multiply both sides by 1/2, that would get me what I'm looking for. So my substitution for t dt should be 1/2 du. So tack that on there, 1/2 du, and integrate that. 1/2 e to the u du is what we would be integrating, which ends up being, by rule, 1/2 e to the u plus some integration constant that we would call c. That would be if it were an ordinary Calc 2 problem. However, it's part of a vector value function. So I would say equals, so my first component is going to be 1/2 e to the t squared plus c sub 1, right? And you could check that out by differentiating, but I don't think you need to, right? The second part is a rule, right? the antiderivative, and I'll just kind of chuck this off on the side too, the antiderivative of 1 over 1 plus t squared dt is equal by rule to the arctan of t plus c. So in this case, it's just saying arctan of t plus c2. And then the last component is just your antiderivative of the sine function. Antiderivative of sine is negative cosine. However, we have that 4t, so we correct for that by multiplying by a quarter. Little old school Calc 2 trick. Instead of doing U substitution for it, you just divide by whatever the coefficient is of the linear function contained within the trig function. So then that's telling me to tack on a C3, and that's my antiderivative. Right. And with the last couple of minutes we have, what I'll do is like I said, we're just going to ditch this one for now. Doesn't really bring anything to the party. We'll do D on the calculator, the Desmos calculator, because all you're doing is integrating that piece by piece. All right. So we're looking for the antiderivative over 0 to pi, over the interval 0 pi over 3 of sine 2t dt. We also need, over the same interval, tangent of t, and over the same interval, e to the negative 2t. All right. And so whatever we get as a result here is going to be the coefficient of I, the coefficient of j, and the coefficient of k. So it's just a matter of crunching that out in the calculator. That stuff I don't ask you to do by hand. Right? Anything that involves definite integration, you don't have to do by hand. So 0 to pi over 3. Sine of 2. I'll just use x. Oh, get out of here. We'll just use x. Close it up. dx. 0.75. It's surprisingly clean 0.75. So 3/4 I. Then the same thing, just with the tangent of this. I'm using x here, so now this one is a decimal value, pretty ugly, but that's fine. You know, when I say that you could do it on Desmos, you could do it on Desmos. If you want to come up with an exact answer, that's okay too, but it's not necessary is what I'm getting at. Because, you know, like the antiderivative tangents, you know, in this case, it would be t tangent t minus t. But, oh, actually, no, actually, I was sorry, I was thinking the natural log. That was weird. The natural log of secant of t, something like that. Anyway, so plus 0.693, that's good enough, is my j. And we're going to get a most likely a decimal anyway when we do the exponential e, so you know it's perfectly fine to give decimal answers, right? When it comes to the definite integrals. So e raised to the negative 2x, and so we're looking at about positive 0.483. 438, I just spelled it backwards. And that would be K. Now I kind of feel obligated to make that a 0.75 just to keep it looking consistent. All right, but decimal form notation is perfectly fine. All right. There was a time and place for evaluating all this stuff by hand. That was Calc 2. You know, it's double jeopardy if I assess you on that again. All right. Or at least that's my philosophy. Some people don't think that way. I don't care what they think. Like I've said repeatedly. All right. So I am going to stop the recording and